Okay. So last week we were talking about entropy as a measure of uncertainty, as a measure of chaos in a given system, and then at the end we were started talking about coding. Now, just a quick recall. A code of a random variable is an assignment which encodes the values of that random variable using strings from an alphabet. Most often we will be using just an alphabet which is binary, meaning zeros and ones. So we have a random variable which has some values, let's say x1 up to xn. They come up with some probabilities and we encode them using some code words, for example 000, 001, 10, and so on. And then we want to find out what are the lengths of the codes, the individual codes. So here the length of code 000 is 3, the length of code 001 is 3, the length of code 100 is 2. And if we want to find out what the average code length, the expected code length, is denoted as L of C, and it is the sum over all possible values, the length of the code times the probability. Okay, the expected code length. Now, today we will see how the expected code length is related to entropy and how to find codes of random variables which are more efficient than others. We have seen last time, I maybe even show it here, that there exist several classes of codes. Some of them are more useful than others. If the code is by itself and not invertible mapping, meaning that it is singular, it's not that useful, because if we send somebody a symbol, he does not know how the symbol gets decoded. So we want codes which are non-singular. But also we need the whole concatenations of such strings to be uniquely decodable, so that we are not in doubt which message actually was sent in the terms of values one after another. So we focus on uniquely decodable codes. And among uniquely decodable codes, the most useful and instantly recognizable is the class of instantaneous codes, where no code word forms the beginning of another one. If you have a code which is instantaneous, you can decode it as you get the individual values one after another, and you can work. It can be shown that instantaneous codes have several important and quite useful properties. Now, let's take a look first at a couple of theoretical results, which will then help us later when building the actual codes. So let's just label it by coding theory. First of them is the Kraft inequality. This helps us if we restrain ourselves only on the codes which are uniquely decodable. It helps us to find a relation between the individual code lengths and how they, well, and postulates us an inequality, which helps us then further to find out the optimality of the code. So suppose we have a random variable with values x1 up to xn. We encode it somehow using an instantaneous code from a D-array alphabet, for example, a binary or ternary or whatever alphabet we like, and we just take the lengths of the individual code words. Then it holds that if we take a sum of d to the power of minus code lengths, we get something which is less than or equal to 1. And other way around, if we have an n-tuple of such code lengths, then there exists an instantaneous code with some code words with those code lengths. So for an instantaneous code with code lengths Lx1 up to Lxn, it holds that sum over all i's d to the power of minus Lxi is less than or equal to 1. Instantaneous D-array code. By this we mean binary, ternary. D is just the number of symbols which we use for encoding. I'll maybe use something better than red, right? Now, proving this is not that difficult as it might seem. Maybe this one. Not this one. If you think about a code as a tree, let's take a look. Think about last time when we were trying to establish or just visualize a code or entry of a random variable using a binary questions tree. Zeros and ones, counting how many questions do you need to get to a value of a random variable. Now, if you look at such a binary tree and you'll see individual code words as the node of the tree, here we start at each splitting. This is code word just 0, then we have a code word 1 0 1 1 1 and so on. What we can do is think of the depth of the tree. If it's a binary tree with a depth of 1 2 3, what's the number of nodes in the last depth?
Number of depth minus 1. No, the number of branches.
The number of branches.
The power of minus depth minus 1.
Yeah, so we have at each point we have 2 branches, so 2 to the power of the number of depths, right? So 1 2 3 depths. So we have 2 to the power of 3, which is 8 nodes at the end. 2 2 2 2 2 2. Yeah. And if we think about, so that's the number of nodes at the last depth. Two to the power of the depth of the tree. So in a general case where we would have a D-array alphabet, it would be D to the power of, let's say, L maximum. Okay, and now if we compare this to the number of descendants of each of the code words, then we'll see that this is always larger than or equal to the number of last depth descendants of each of the code words. Okay, we'll go through the individual code words and progress them until the last depth. Now this has, on the last depth, it has 1, 2, 3, 4 descendants. This one on the last depth has 1, 2 descendants. And this one is already on the last depth, so it is itself on the last depth, so 1. So the number of descendants of all the code words together is 1, 2, 3, 4, 5, 6, 7 in this case. And if we formalize it, then for each of the code words, the depth, how far we go, is the maximum depth minus the original depth. So here we go just 2 levels down, here we go 1 level down, here we go 0 levels down. And if we add, so number of last depth descendants of all code words is, well, sum over all, well, possible values, d to the power of the maximum depth minus the actual depth, so Lx. And we know that this, the number of nodes at the last level, is always larger than this. Okay, because sometimes we have a code word here, sometimes we don't at the last node. Here there is nothing, so it's 8 larger than 7 because there is no word on this node. It can never, the number of descendants of the individual words is never larger. So we have that d to the power of maximum depth, so the maximum length of any of the code words, is larger than d sum over all x's, d to the power of, well, the difference between the last depth and the depth of the code word. And if we work out this inequality, so sum over x, d to the power of L maximum, this is basically d to the power of minus L x being less than or equal to d to the power of L maximum because of how powers behave, right? This does not depend on x, so we can put this outside, and then we can scratch it out and get 1 here, so we'll get the original inequality. So for any code which is instantaneous, this inequality holds. Now, it might seem rather technical, which it is, but we will use it to find the relation between entropy and code lengths of the expected code length. Now, first, does it make sense? Now, this holds for any instantaneous code. So, code where no code word is the beginning of another. Now, it can be proven, that's a bit harder to do, that this also holds for not just instantaneous codes, but also for all uniquely decodable codes. So if we have a uniquely decodable code which is non-instantaneous, it doesn't bring into the fold anything better than the instantaneous codes, which we'll see later on how this is actually, for what this is actually good. And it can be proven that for any code which is uniquely decodable, we can, by switching out zeros and ones or switching out some code words, find an equivalent instantaneous code which would encode the variable more practically. Okay. And now we use this to prove how it works, how it puts into relation the entropy and expected code length. So, theorem for an instantaneous d-array code of X, it holds that L of C, the expected code length, is always larger than or equal to the entropy of X with logarithm base G. So if you have a random variable with given values, with given probabilities, and want to encode it in some way using an instantaneous code, the expected code length will never be smaller than the entropy. So regardless of how you optimize your code to be, how you optimize the code lengths, there is a bound which you can never cross. This is what you can then try doing in your homeworks for a random variable which represents the proportions of letters in an English text. Okay. Now, another thing is that the equality holds only if the probabilities are expressed as d to the power of minus code lengths. Okay, now how to prove this? It's actually quite easy, first by using this and then by using another result from what we have seen last time. I will go through the proof a bit more in depth so that we see how this works out. Now, let's take the expected code length and subtract the entropy. And see that this is larger than or equal to 0. Now, the expected code length is sum over all x's probability of x times the code lengths minus, and now the entropy is minus sum over all x's probability of x times logarithm d-array logarithm of probability of x. Okay. Now, let's rewrite this code lengths into a logarithm, which is here, applied and then applied on the power of d. We know that the logarithm of d to the power of x is an inverse function. So this one is actually the d-array logarithm of d to the power of L. And
Now what I wanted to do was put a minus there. So what I will do is first, sorry about that, first I will switch those two and I will see that this is basically sum over all x's, probability of x, logarithm of probability of x. And now minus sum over all x's, probability of x minus Lx. This minus gets here and there. And this one is the d-area logarithm of d to the power of minus L of x. And now let's replace this with something which adds up to 1. Because if we take the d-area logarithm of d to the power of minus Lx over a constant which is the sum of these, d to the power of minus Lx, then we get something which is addable to 1. So some type of a distribution, let's say Rx. Okay. And then I will take this logarithm and say that this is a logarithm of Rx minus the logarithm of C. Right? Because the logarithm, plus logarithm of C. Because the logarithm of product is product of logarithms. Then I break down this part and I get that this is sum over all x's, probability of x, the d-area logarithm of probability of x, minus sum over all x's, probability of x, d-area logarithm of r of x, and now minus sum over all x's, px times d-area logarithm of c. Huh. I can take then this first two parts and put it into one sum. Take px out, and then I will have logarithm of px minus logarithm of rx. So that's a logarithm of a division. So this is sum over all x's, px times logarithm of px over rx minus, and now I have sum over all x's, px times a constant. And now what happens if I take probabilities of some distribution and add them up all together? What do I get? 1.
1, sure. So this is 1, and the only thing I have here is just the d-area logarithm of c. Now this is, all of those are d-area logarithms. But what do you see as this part? Sum over all x's, probability times the logarithm of one probability over the other probability with respect to a distribution R. Remember last time?
It's a probability A with respect to B? Maybe no.
Not really. This would work if we had here the joint distribution and here the conditional distribution. But here Px is the original distribution regarding the values concerning the individual possibilities for x, and Rx is a different distribution. So this is the relative entropy between Px and R. Okay? Minus the logarithm with base t of C. And C was sum over all x's d to the power of minus Lx. Okay. And now from the Kraft inequality, we know that this is less than or equal to 1. Okay, and if you apply a logarithm on something which is less than or equal to 1, what do you get?
Minus.
Something which is negative, right? Or at most equal to 0. Okay, so this whole is larger than 0, and we subtract it from something, so we get something which is this whole with this minus is non-negative. Okay, and now this is a relative entropy, and for a relative entropy of any two distributions, we know that it is also non-negative. This is what we have proven last time. Okay, so this part is non-negative. This part is non-negative. We add up two things which are non-negative. So we see that this is non-negative. So at the left-hand side, we have the expected code length minus the entropy. And on the right-hand side, we have that this is larger than or equal to 0. So this means that this is larger than or equal to this. Okay, and when is this, when does the equality hold? Now the equality holds whenever, well, this is equal to 1, because then this logarithm is equal to 0. So equality if, well, sum over all x is d to the power of minus Lx is equal to 1. And P is equal to R for all x's. And what is R here? The R was d to the power of minus Lx over C, which is equal to 1. So d to the power of minus Lx. Okay, so whenever the probabilities regarding a variable can be expressed as the base of the alphabet to the power of minus code lengths, then it is a code which is optimal and reaches the entropy. Does it make sense? Now the trick is, if you have, which we'll see in a short while, if you have a distribution where the probabilities cannot be found in such a form, so this relation is not equal, we need to be a bit creative. For example, if we have a distribution where we have three possible values, some of them with probabilities 1/3, 1/3, 1/3, then we cannot encode this binary in a binary way so that the equality would hold. So we need to work in a different way. Now, if Px is equal to d to the power of minus Lx, we apply the dRe logarithm on both sides. The dRe logarithm of the probability is equal to minus Lx. This means that the code lengths are equal to minus the dRe logarithms of P. And you can imagine that depending on what the probabilities are, this logarithm might not be an integer. And we cannot have non-integer code lengths. Yeah, the code length can be either 1 or 2 or 3 or whatever. It cannot be 1.5 symbol. Okay, so if possible, use this. And if it's not possible, we can use, well, the upper part. And we'll get an integer number. We'll see that if we would take this coding for each of the values, we wouldn't get an most efficient coding, but we get an upper bound on the expected code lengths. Yeah, because if we think about that, then for the Kraft inequality, this code lengths are smaller than the optimal ones, and if we insert them in here, we'll get something less than the original parts in the Kraft inequality, getting us 1, and we can see that for any code, that we can always construct a code for which the code length of all words will be larger than or equal to minus the dRe logarithm of Px and less than the upper part, which at most is equal to that plus 1. So it is always less than minus the dRe logarithm of P plus 1. And now if we multiply all parts of this inequality by Px and take a sum, we'll get that minus sum over x probability of x logarithm of probability of x is less than or equal to sum over all x's, all x Px. minus less than minus sum over all x's px logarithm px plus 1 times, well, sorry, sum over all x's 1 times px. And in the middle, we have the expected code length, LC. On the left-hand side, what do we have? Minus sum over all x's px logarithm px. That's what?
Entropy.
That's the entropy, right? And here, that's also the entropy. And here we have 1 times probability sum over all values. So plus 1. Okay? So we can always construct a code which has its expected code length between entropy and entropy plus 1. Okay? So even if the probabilities cannot be expressed in such a way that the code length would be corresponding to it in that way, we'll always get at most entropy plus 1. Now, such a code, which is optimal among all codes and fulfills this, is called a Shannon code for the Shannon. For Claude E. Shannon, who basically invented the modern coding and information theory. Does it make sense? Okay, so let's take a look at a couple of exercises so that we get the hang of this. That's exercise 4.4. Suppose that we have a random variable which can attain 4 possible values. Suppose we know what are the probabilities of them happening, and suppose that somebody has taken the liberty of suggesting a code for us. And we want to use this code to decode a message and find out where this code is actually optimal. So, encoded using binary. I'll put that as follows. X, Px, Cx. 1, 2, 3, 4, 1/2, 1/8, 1/4, 1/8, and Cx, the code here is 0, 1, 0, 1, 1, 0, 1, 1, 1. And first we want to decode a received message. Decode message 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0. Okay, now the good thing here is that the code is instantaneous. No code word is the beginning of another. So we can go from the left to the right, and whenever we find out a string which actually is a code word, we can immediately decode it and move on. So we go from left to right. And immediately we see a 0. Oh, good. So a 0 is encoded as 1. Then we see 1, that's not a code word, 1, 1, that's not a code word, 1, 1, 0, that's a code word, and the corresponding value is 3. Then 1, that's not a code word, 1, 1, 1, 1, 1, that's a code word, good. So that's 4, 1, 0, that's a 2, 0, 1, that's a 1, and 1, 1, 0, that's a 3. Okay, so because the code is instantaneous, we do not need to worry about waiting for the next bits. Immediately, whenever we encounter a code word, going from left to right, we see that we can decode it and get the original result. Does it make sense? Mm-hmm. Good. Now let's compute the entropy of X. So that's B. So, yeah, we are working with binary entropy, so we want to find the binary entropy. So minus sum over all x's probability times logarithm of probability. Now we have seen such a distribution, so we'll just go over the all possible values. So we have minus 1/2 logarithm 1/2 minus 1/8 logarithm 1/8 minus 1/4 logarithm 1/4 minus 1/8 logarithm 1/8. Now those are binary logarithms, so to which power do I need to take 2 to get the argument? So what's the logarithm of 1/2?
Minus 1.
Minus 1. Logarithm of 1/8?
Minus 3.
Minus 3. That's the same here. And here minus 2. So what I have is 1/2 plus 3/8 plus 2/4 plus 3/8, which is like, this is the same as 4/8, this is the same as 4/8, so we get 7/14/8, so 7/4. That's the entropy of X. And now we want to find the expected code length. The expected code length is sum over all values, the length times the probability. So if I here sketch out the lengths, here the length is 1, here the length is 2, here the lengths are 3 and 3. So I get that it is 1 times 1/2 plus 2 times 1/8 plus 3 times 1/4 plus 3 times 1/8. So I get 1/2 plus 2/8 plus 3/4 plus 3/8. This is like 6/8. This is like 4/8. So I get 4, 5, 6, 12 and 3 is 15 over 8, which is, well, larger than the entropy. Okay, so if we use this coding, the expected code length is 15 over 8. Now, does it make sense? Good. Part D asks us if this code is optimal. Well, obviously, it does not seem so. And how could we fix it to get a better expected code length? We have the probabilities fixed, but whether we could suggest a different encoding.
We could decrease the length because we have only 4.
Okay.
We could use only 2 bits.
Yeah.
So, how could we do that? What do you suggest? How could we encode the individual levels?
0, 0.
1, 0.
Okay, again.
0, 0.
0, 0.
1, 0.
1, 0.
0, 1.
0, 1.
1, 1.
1, 1. Okay, so let's call it C with a, yeah, just, how do you call it? Stroke?
Prime.
Prime.
Yes,
Prime, yeah, so let's call it C prime. Then, what's the expected length of C prime? So sum over all x's, the length times the probability. I will just write down C prime times the probability. So we have like 2 times 1/2 plus 2 times 1 over 8 plus 2 times 1/4 plus 2 times 1 over 8. So this is 2 over 2, that's 1, plus 2 over 8, plus 2 over 4, plus 2 over 8. No, this is 1/4, this is 1/4, this is 1/2. So we get 2, which is even worse than that.
It's not even Shannon.
It is a Shannon.
But it's bigger.
Careful. It is actually not, for one reason. The first part has a probability of 1/2. So it doesn't make sense to take such, well, often a recurring value and encode it using 2 bits, right? In that case, we wouldn't have, well, the logarithm of of the probability would then not be equal to that. Now, could we take an even better code than the first one?
Well, if the often ones, as you said, should be of the least number of bits, then we could 1/2 could stay the same, 1 bit.
Okay.
1/4 could change because it's using 3 bits. And the longest one would be 1 over 8.
Uh-huh.
So it's like 0, maybe 1, 0, 0 for the second.
So let's take 0, then 1, 0, 0,
And then maybe 1, 1,
1, 1, yeah, and then
1, 1, 1. Leave it like that.
it wouldn't be instantaneous.
0, 1, no.
Yeah, 1, 1,
So
0.
let's just switch those two, right?
Yeah.
So take 1, 0 and 1, 1, 1. Now, the interesting thing here is that if you take the lengths of this code, we have 1, 3, 2, 3, And if we take 2 to the power of minus code length, so 2 to the power of minus 1, 2 to the power of minus 3, 2 to the power of minus 2, 2 to the power of minus 3, which is 1/2, 1/8, 1/4, 1/8, you see that this is the same as the probabilities. So for this code, this C double prime, the condition for the expected code length being equal to the entropy holds, so it is the optimal code. Okay? So must be the optimal code. And if we take a look, immediately we see L with C double prime, C double prime X times Px. So we have 1 times 1/2 plus 3 times 1/8 plus 2 times 1/4 plus 3 times 1/8, which is basically the same as we had here for the individual parts are the same parts as for the entropy. Okay, so we get 1/2, that's 4/8 plus 3/8 plus 4/8 plus 3/8. So altogether 14/8, which is equal to the entropy. Okay, so in such a case, when you see that the probabilities of individual possibilities are actually powers of 2, in this case negative powers of 2, right, for them being probabilities, then you can immediately say what will the optimal code lengths be, right? The optimal code lengths will be actually minus those logarithms. Okay? You then can decide where you put zeros and ones, and keep in mind to get an instantaneous code. But other than that, if you keep those lengths, you get an optimal code.
By the way, how we got to know that it is the code length is not optimal? The first question of the D part, is the code length optimal?
Okay, we see, we see that it is, not equal to the entropy, and we see that there is another code which has smaller code length. Okay. Because there exists such a code where the code lengths fulfill this equality. Okay? So d to the power of minus code lengths is equal to the probabilities. If there exists such a code, then this one is optimal, and all the others which have longer code lengths are not. Okay?
Is there always an optimal encoding for any number of possible random variable assignments?
There is, but it doesn't always reach the entropy. Optimal means having the lowest code length among all. So yes, we can always find one which is the best, and there are none better, but they don't always reach the entropy.
Okay, yeah, that was my question. I just didn't know how to ask it.
So let's take a look at the next exercise. Yeah, suppose we have 4.5. Suppose we have again
a random variable which we want to encode using binary alphabet. Suppose that the variable has 3 possible values occurring with equal probability, 1/3, 1/3, 1/3. So let x have binary code as follows. X one, 2, 3, 1/3, 1/3, 1/3. And Cx is 0, 1, 0, 1, 1. And we want to find the entropy, we want to find the expected code length, compare them, and find out whether this code actually is the most optimal. So, A, find the entropy. The entropy, again, is minus sum over all x's probability of x times logarithm of the probabilities. Now here we have minus sum over all x, 1/3 times logarithm of 1/3 minus 1/3 logarithm 1/3 minus 1/3 logarithm 1/3. Now we have 3 times the same, right? So we have like 3 times the same thing, 1/3 times, and now logarithm of 1/3 is like minus the logarithm of 3, so these minuses cancel. So this is the logarithm of 3. That's a binary logarithm of 3 because we are working with a binary code, binary entropy, and this we cannot compute just right away. We need to take a computer or a calculator, and the binary entropy is, I have it, oh, I don't have it here. I have it here actually, sorry. That's actually 1.58 about. Yeah, the binary logarithm of 3. Okay, now. Yeah, that's the logarithm with base 2.
Yeah, this calculates this base time.
Okay, now at the exam you just can leave it as it was, right? Now, the expected code length is sum over all x's length of the code times the probability. Okay, so let's just sketch the length of the codes. 1, 2, 2. Good. So that's 1 times 1/3 plus 2 times 1/3 plus 2 times 1/3. So 1, 2, 3, 4, 5 over 3. Well, that's 1.66 periodic, right? So, as for part C, we see that the length of the code, the expected code length, is larger than the entropy by a bit, or by a small amount.
but not equal. Now, if you look at this case, could we construct a binary code where the expected code length will be smaller?
But they're all equal probability. So we could maybe do 1, 0, another 1, and third just, I don't know, 1, 0, 0, 1.
But it will be the same expected length. It will still be 1, 2, 2 for everything.
Yeah. We cannot do it in that way, so here we would have 0, here we would have 1, and here's something else, because it wouldn't be an instantaneous code. Yeah? And we want to construct an instantaneous code, so we need at least 2 of them have the length of 2. We cannot have 2 of them have the length of 1. So it is not possible to decrease the expected code length. Now, for the entropy to be equal to the expected code lengths, we would need the probabilities to be equal to, well, d to the power of minus Lx for all x's. Here d is 2. So this means that the logarithm of px needs to be equal to Lx, so minus logarithm of px needs to be equal to Lx. So Lx needs to be equal to minus logarithm of 1/3, which is equal to 1.58, which cannot be. This is not an integer, and we cannot have non-integer code lengths, right? We cannot have just 1 and half of 1, right? Okay, so in this case, we cannot construct a binary code reaching the entropy. Okay. Any questions to that? Now let's take a look at another exercise. My colleague who actually made those slides for the Czech course was searching for outfits for his kids and found this thing which doesn't look like anything at all or everything at once, and he built an exercise around that. Now suppose we asked some people, and what is this? And we counted the number of replies. Some of them said it's a donkey, some of them said it's a dog, some of them said it's a fish, and so on and so on. And we counted, well, suppose that this thing is actually equal to what's the result, with the probability given by the actual proportions of answers. So suppose that this is actually a random thing, which is either a donkey or a dog or a white thingy or a blue thingy and so on, with these probabilities. And we want to construct a code, a binary instantaneous code,
for this random variable using branching questions, which would be first natural ones. So 4.1 plus x b random variable with values and probabilities in this table. 1 donkey, 2 dog, 3 fish, 4 snake, 5 white thing, 6 blue thing. And probabilities being 1/2, 1/8, 1/8, 1/8, 1/16, 1/16. And first, we want to construct a coding using natural branching questions. Natural language. Branching questions. Yeah, the assignment leads us to using questions like whether it is an animal, whether it is a mammal, and so on and so on. So let's try doing this and see where it leads us. So, is it an animal? That's our first question. If the answer is yes, we start our code with a 1. If the answer is no, we start our code with 0. Now, if the answer to whether it is an animal is yes, then we can ask whether it is a mammal. If the answer is yes, we start our code with a 1. If the answer is no, sorry, not start, we continue our code with a 0. Now, if the answer for whether it is a mammal is yes, we have restricted ourselves only on those 2 options. So now what we can do, we can just ask for one of them. So let's ask whether it is a donkey. If the answer is yes, we follow our code with a 1, and we know that's a donkey. If we get a no, after this set, we follow our code with 0, and we know that's a dog. So the code words can then be written from back to end 1, 1, 1, 1, 1, 0, and so on. If we get a no for whether it is a mammal, we then ask whether it is a fish. If we get a yes, we know that it is fish. Follow with a 1. If no, follow with a 0. And we know that's a snake. So we get 1, 0, 1, 1, 0, 0.
And if the first answer to whether it is an animal was no, we are just operating on this part, white thingy, blue thingy, and we just ask whether it is one of them. So just ask whether it is white. If yes, then we follow our code with 1 and see that it is white with the code word 0, 1. If no, we follow our code with 0 and we know that it is blue. So 0, 0. Okay, in this way, the yes-no questions lead us to an instantaneous code. Yeah, because we are at each of the branching, we are splitting the set into disjoint parts. Okay, so no code word can form the beginning of another because that would be on either further on that branch, which is not possible, or we would move to another one, also not possible. Okay, so this yes-no questioning leads us to such a code. Now, if we want to compute the expected length of such a code, so find the expected length of such a code. Now, the expected length is sum over all values, the length times probability. The length here is 3, 3, 3, 3, 2, and 2. So we have like 3 times 1/2 plus 3 times 1/8 plus 3 times 1/8 plus 3 times 1/8 plus 2 times 1/16 plus 2 times 1/16 and 3/2. This is like 3 times 4/8. And this one is like 1/8, this one is like 1/8. So we have 12 plus 3 plus 3 plus 3 plus 1 plus 1/8, which is 15, 18, 21, 22, 23/8, which is 2.875 bits. So on average, we need 2.875 questions to get to the result. Now, is such a code optimal?
No.
Doesn't seem so, right? What seems to be the problem?
The one with the highest probability has one of the longest lengths.
Yes, exactly. The branching questions are natural. They seem to divide our field of options into logical subsets. That's good, but it is not efficient. What would be the first, if we want to proceed efficiently, what would be the first question which we would ask?
Is it a donkey?
Is it a donkey? If we have a yes, then we have a code word of length 1, which happens with half of the probability. Okay? Now we also know from what we have learned today that if the probabilities are corresponding to negative powers of 2, which is the case here, we immediately can take the code words in an efficient way, the lengths of the code words corresponding to the individual probabilities, right? So to get an optimal code, we need the lengths, well, the probabilities to be equal to 2 to the power of minus Lx for all x. So this means that Lx needs to be minus logarithm of the probabilities. So here x, px, and L optimal of x. Here we have 1, 2, 3, 4, 5, 6, 1/2, 1/8, 1/8, 1/8, 1/16, 1/16, and here 1, 3, 3, 3, 4, and 4. Okay, and now we can conjure up any code we like with keeping in mind that it needs to be instantaneous. So, for example, we encode 1 as the donkey as 1. So this corresponds to the first question, whether it is a donkey. Yes, giving us a donkey. And no, requiring us to ask something else. And for here, having lengths of 3, 3, 3, and 4, 4, we just need to take something which begins with 0, because it cannot begin with 1 to get an instantaneous code. And the other 2 bits we can assign however we like. So let's say 1, 1, 1, 0, 0, 1. And here we have the lengths of 4, so they need to differ on the 4th bit. So 0, 0, 0, 0, 1, and 0. Okay. So then the other branching question on the 2nd bit will be, well, is it a dog or a fish? If yes, then we continue with 0, we ask whether it is a dog. If yes, we continue with the 1, we get that it's a dog. If no, we continue with 0, and it is a fish. Right? And this happens with a probability of 1/8, 1/8, and we need 3 questions to get to the bottom of that. If the answer to whether it is a dog or a fish is no, this means that the 2nd bit is 0, we are right here, and we need to ask about the 3rd bit. In the 3rd bit there is a snake and a white and blue thing, so we ask whether it is a snake. If yes, then it's a snake. We continue with 1. If no, we continue with a 0 and need to ask whether it is white thing. And if yes, we continue with 1, it's white thing. If no, we continue. Yes. 1, no, 0. Okay. Okay, so this is the most efficient order of questions. It does not seem natural from the first glance because it does not divide the options into naturally put groups, but it separates them according to the best probability, giving us the optimal code length. Okay? So in this case, the code length C optimal is, well, 1 times 1/2 plus 3 times 1/8 plus the same, so times 3 plus 4 times 1/16 again and again, so times 2, getting us, well, 1/2. This is like 4/8. This is like 9/8. And this is like 8/16, which is 4/8. So we get 4 plus 9 plus 4/8, which is 17/8, which is 2.125 bits. So this is the ideal expected number of questions. If we'd like to make sure that this actually is equal to the entropy, we could just compute the entropy Hx, that's minus some probability times logarithm of probability. That's minus, well, 1/2 times logarithm 1/2 minus, and now we have 3 times 1/8 logarithm 1/8 minus 2 times 1/16 logarithm 1/16. Now this is minus 1, this is minus 3, this is minus 4, and we will get the same thing. Yeah, this minuses get cancelled, and this one corresponds to this one, this 3 corresponds to this 3, this 4 corresponds to this 4. So we'll get the same 17/8, so it is equal. Okay, does it make sense?
Yes.
Good, so here we see the relation between the entropy and the information value, the code length, and so on. Any questions to that? Yeah, so we end for today, and on Wednesday we see how we can construct an optimal code using a known algorithm. Maybe you have seen Huffman code or Huffman algorithm on other subjects. Yeah, you did. Good. So we'll see how this can be done once again.
Okay. And what is the costume supposed to be? Like the URL is right there. Does it say like what kind of animal or?
It's actually a unicorn.
Yeah.
But it has what? It has a blue thing that confuses me. It's supposed to be.
Es un vestuario, güey. Es el costume.
Es un costume.
Yeah, this is actually, yeah, it's actually, I think it's actually sold as a white blue unicorn.
Well, that's just cheating.
Yeah.
Also, I have a question about the Marast
Yes.
platform. Remember last class that I was asking you about how to input the answers?